I'll present uKnit, a position-aware reconfigurable machine-knitted wearable for gestural interaction and passive sensing using electrical impedance tomography. Inspired by gaiter scarves, multi-purpose tubular scarves that can be wrapped, folded, and scrunched to put on different places of human bodies, we built uKnit, a multi-purpose soft-wearable device that affords reconfigurability and adapts to different uses. For a user who has one device for each different context and application, they would need to carry several distinct devices throughout the day, even when they're not needed at the time. Prior works on woven capacitive touch sensing integrated into garments, customizable electronic bandages, and machine-knitted pressure sensing interfaces show promising functionalities of soft wearables. However, most soft wearables are rigid in their form factor and utility. Prior works have explored multi-purpose touch-sensitive braid, but it does not afford frequent location changes. Detachable smartwatches explored reconfigurabilities of wearable technologies, and the smart handkerchief enabled deformable and reconfigurable tangible interaction. Here, we want to explore a reconfigurable wearable that is soft, comfortable, and conforms to a user's body that can be significantly more customizable than a watch, particularly in terms of form factors, worn locations, and interaction modalities. Thus, it can offer a wider range of capabilities. To enable this vision, uKnit has the following design requirements. Maximize the resemblance to an ordinary accessory so that the wearable remains familiar and affords reconfigurability. Ensure the wearable is optimally sized, such that it is large enough to be worn comfortably around the waist, but not become bulky after multiple wraps. Minimize the number and sizes of hard components so that the device remains flexible and easily reconfigurable. Supports a wide range of sensing capabilities to enable different applications in different configurations. Knitting is a popular fabrication technique used in accessories, and knitted fabrics are stretchable, thus meeting the first two. To meet 3 and 4, we chose electrical impedance tomography as the sensing technique to minimize the number of wires and rigid components while enabling a large interaction area with multiple sensing capabilities. In this work, we present uKnit, a knitted wearable that can morph into different functional forms and afford unique spatial awareness. In summary, we contribute a process to prototype a novel reconfigurable machine-knitted soft wearable sensor with spatial awareness using off-the-shelf yarns, validation of electrical impedance tomography on anisotropic knitted resistive fabric, machine learning models that show the feasibility of on-body localization, gesture recognition, and passive sensing, and finally, example applications and demonstration of uKnit's utility in a wearer's daily life. First, let's start with the prototyping processes. We first use an industrial V-bend knitting machine for scalable, repeatable, and programmable fabrication. In this video, we see 3 carriers are in use. Ones on the sides are for the resistive yarn, and the one in the middle is for the normal insulating yarn. 2 carriers are needed for the resistive yarn so that the 2 areas are completely disconnected without any post-processing like cutting. In the bottom, it is a smaller version of the knitting program visualized using the knit-out visualizer. Each color represents yarn path by a carrier. At this line, the thinner blocks colored in light blue, dark blue, purple, pink, and red are all the top green insulating areas, and the wetter blocks colored in orange, neon, yellow, green, and teal are the top gray conductive areas. There are 9 of them and thus requiring 9 carriers. This technique where areas of color are incorporated is called intarsia. The machine has 10 carriers in total. We use the last carrier for decorations, used in the highlighted blue areas on the left. Textiles has a history of being means of expressions for cultures and identities. The capability and freedom of customization is valuable. All of the yarns used are off the shelf. The gray conductive yarn is a Beckinox polyester blend with a specified resistance of 20 ohm per centimeter. For the connector, first we harvest a washer from the ring terminal, wrap thin enameled wires around it, solder the wires to the washer, and then glue the washer to the conductive fabric using conductive epoxy. This is better than gluing wires to the fabric directly as it increases the contact area. The floor patch layout is connected to a sensing board via glued connectors and routed in serpentine traces. Then let's understand the electrical impedance tomography signals with anisotropic knitted resistive fabrics. Before we talk about chosen sensing principle, electrical impedance tomography, EIT, let's first look at impedance. Impedance is the sum of resistance, capacitive reactance, and inductive reactance. In our system, we can omit the inductive components. So with EIT, uKnit is able to capture both resistive changes induced by deformations and capacitive changes induced by conductive objects such as fingers. EIT is a non-invasive imaging technique to infer internal conductivity characteristics. It was first proposed for medical imaging in 1978, and in recent years, it gained traction in the HCI community for a wide range of applications. In the right image, we can see alligator clips clipped around the borders and the inferred resistance distribution correlated with pressure distribution. In our system, electrodes are placed along the borders of each patch, AC currents are injected between adjacent pairs of electrodes, and the voltage differences between the 5 other pairs of adjacent electrodes within the patch are measured. Each patch is disconnected from each other, and this driving pattern gives us 160 channels of signals in total. Now let's talk about how knit sensing works. Though in this work, we don't focus on stitch-level circuit models, but looking at a simple one gives a good intuition on electrical property changes when shape changing occurs. Be reminded that knitted fabrics are constructed using continuous yarn. So when we look at the resistance of the yarn, there are yarn resistance and there's contact resistance. Due to loop structures, when one loop is pulled through another, there is contact resistance between the two loops. Prior works have suggested that contact resistance dominates the changes when strain and pressure applied. Here are the conjecture effects of some of the gestures. Touch induces local changes in mostly contact resistance. A directional stretch induces changes in both yarn and contact resistance. Grab is essentially a touch with a larger area, and pinch is like multi-directional stretch. Our relative impedance change experiment with an oscilloscope further showed that gestures induce significant amplitude changes as shown on the top row, and small phase shifts as shown in the bottom row. Now that we have these signals, we condition and model them and validate our algorithms with user studies. To train the machine learning models and evaluate the system, we conducted user studies with 10 participants. First, let's look at the algorithms for location detection and gesture recognition. For each channel, with the collected sample size, we calculate 9 statistical features. And the aggregated features for all 160 channels are inputs to the random forest classifier with scikit-learn default parameters. Using the trained machine learning models with just a simple gesture like touch, uKnit is able to detect its configuration and location. With 88% accuracy for a within-user model and with 78.2% accuracy for a cross-user model. Once uKnit recognizes the location, it can also recognize different gestures. Let's take a look at this video of live predictions. We trained a random forest model for 7 gestures and achieved 90.3% accuracy for a within-session model, 80.4% accuracy for within-user model, and a 75.4% accuracy for cross-user model. Then for passive sensing tasks of sensing the wearer's respiratory rate and body posture, we first condition the signals to filter out low and high frequency components. Then the most sensitive signals are selected. For respiratory rate estimation, we count an average number of peaks of selected signals. For body posture detection, we train and predict with k-nearest neighbor classifiers for each signal channel, and the final prediction is the majority vote across all channels. Here are 3 examples of the original and conditioned signals. uKnit's algorithm recognized respiratory rate with an average error of 1.25 breaths per minute and detected a user's body posture while sitting with an accuracy of 86.2%. Finally, let's look at some example applications. We implemented real-time predictors to demonstrate uKnit's potential as a reconfigurable wearable. Gestures are mapped for controlling and logging, and we show examples of a headband or neck scarf music player, a knee bend squat counter, and elbow bend recipe scroll controller.